In the last video, I showed you this, the schematic for our cluster computer. Isn't that exciting? If you watched the last video, you'll notice that this schematic is really pixelated. And there's a very good reason for that. We don't want to look like idiots. You see, we got the problem that, well, we ain't actually electrical engineers. We're just a couple of failed academics. So we're not good enough at electronics to just draw a schematic and then it work. Nah, you see, we have to build it on breadboards first. So what we're going to do is spend the next however many videos, I don't know exactly, building this circuit on breadboards and then fixing the bits that don't work. Because I'll guarantee you, there's probably going to be quite a few bits that don't work. But we'll fix it as we go along. One of the most important bits of the chatter is this bit here. But what does this pixelated lump actually do? Let's have a look at the old paper. That's this paper here. I'll stick a link in the description if you're interested. But anyway, let's look at this bit. Let's read this bit here. Well, blah 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 blah. Basically says we got to make ourselves a binary pattern matcher. So let's do that. What does our pattern matcher do then? Basically, it just tells you whether two numbers are the same or different. And that's it. Now all we need to do is make it with electronics. And to do that, we're going to use our old mate, the XOR gate. The XOR gate has got two inputs, A and B, and an output Q. What happens when we've got a 0 on the A input and a 0 on the B input? We get a 0 on the output. What about a 1 on the A input and a 0 on the B input? We get a 1 on the output. What if we've got a 0 on the A input and a 1 on the B input? We also get a 1 on the output. What happens when we have a 1 on the A input and a 1 on the B input? We get a 0 on the output. Or in other words, if A and B are equal, Q is 0, and if A and B are not equal, well, we get a 1 on the output. So our XOR gate is a 1-bit pattern matcher. But what if A and B are 8-bit numbers? Well then, all you need to do is use 8 XOR gates and then bung all the outputs into an 8-input OR gate. And then, as before, the output will be a 0 if A and B are equal and a 1 if A and B aren't equal. The only thing I found is that 8-input OR gates are quite hard to come by. But luckily for us, 8-input NAND gates, well, they're everywhere, aren't they? So, if we just stick an inverter on the output of all the XOR gates, we can use an 8-input NAND gate instead of an OR gate. Now, let's go back to our paper and look at this bit. In particular, this bit here. Now, it says, watch for a specific pattern of 1s and 0s, which our pattern matcher can do. But it also says it can look at don't cares, which our pattern matcher can't do. So we need to make our pattern matcher ignore don't cares, which is actually really easy to do. All you need to do is change these inverters for NAND gates. So now if we look at bit 0, when X0 is a 1, the NAND gate just acts like an inverter. And when X0 is a 0, well, the output of the NAND gate is always a 1. So we don't care about what A0 and B0 are doing. So we've done it! We've made our pattern matcher. So now we know what our pixelated lump is. It's this. So just to make sure it works, let's build it on breadboards. So for the XOR gates, we're going to be using a 74HC86. And it's got 4 XOR gates, so we'll need 2 of them. For the 2 input NAND gates, we're going to be using the 74HC00. Each of these chips has 4 NAND gates, so we're going to need 2 of them. And finally, for the 8 input NAND gate, we're going to be using the 74HC30. Okay, human man, get the breadboard. Now, stick the 74HC86s on. The human man is just straightening out the pins so it goes into the breadboard easier. So now you're going to stick power and ground on there. Now, human man, get them 74HC00s. Again, he's bending the pins so they're straight, so they go in the breadboard a bit easier. Here's one. And there's the other one. Let's make sure you ain't bent any pins, human man. No, you seem to have done all right there. Now, power and ground. And finally, put the 74HC30 on there. And give him some power and ground too. And that's all our chips on there. Now we need to wire them all together. But we'll do that off camera because no one wants to sit there and watch someone sticking wires in a breadboard, do they? That's boring. So we'll come back when the human man's finished. Oh, human man, that looks alright, miss. Oh well. So what, I'm guessing you've got the yellow ones at A and the orange ones at B. What, so that means the blue ones are the don't cares? Well, go on, human man. Plug it in. Oh, it's working, human man. Now try changing one of them so A isn't equal to B. Yeah, that one there, human man, that'll do. Oh, look, the light's gone out. Now, try the don't care. And look, human man, it doesn't care about what A and B for that one is. But if you change one of the other ones, it does care. Then if you put the don't care for that one. Oh, human man. It's almost like we know what we're doing. Except we don't. Now, the astute amongst you will have noticed that our pattern matcher only does 8 bits. And the ZMOB has 12-bit addressing. So what are we going to do? Well, the chatter is only going to use 8-bit addressing. Because really, I think 256 Z80s is probably enough. I mean, I definitely ain't paying for 4,000, so I think we'll just stick to 8 bits. One final thing about this circuit is that in the future we'll probably find, because of propagation delays, it's too slow. So we'll have to change it to something faster. But for now, we'll just keep it as this. Next time, we'll build some more. I mean, I haven't planned it or anything, so I don't know what bit I'll be making, but we'll make some more of it, don't you worry. I'm going now. Roll, 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 bonk! Let us watch as Jeff flies majestically in his portable toilet, propelled by nothing less than his own torrential diarrhea.